For our first exercise, we have some specific sets A, B, C, D, E, and E given in a specific universe U, and we're just asked to construct the set A union C intersect D. So the first thing we're going to do as an intermediate step is construct C intersect D. So we're going to make a set, and we simply look what things are in C and are also in D. And by and here, I mean the logical operators. So one in C, one in D, those are both true. So the and statement is true, so I'm going to put a 1 into this intersection. 2 is in C, but it's not also in D, so it doesn't go in the intersection. 3 is in both, so it goes into the intersection. Then 4 is in C, but it's not in D, so it doesn't go in the intersection. 5 is in both, so it goes in the intersection. 7 is in D, but it's not in C, so it doesn't go in the intersection. So we're done constructing C intersect D. Now we can go ahead and construct the union of the set we just constructed and A. And for the union, you're looking for things that are in one or the other. So we're just going to list out all the elements of A, B, C, D, all the elements of the set we just constructed, C intersect D, 1, 3, 5. Those are the things that are either in A or are in C intersect D, and we're done. Next up, same A, B, C, D, E, and universe, but we have this more elaborate construction. We've got this union, so we're going to need to construct the thing on the left. Then we're also going to need to construct the thing on the right. So we can go ahead and take this product, A times B, which has nothing to do with arithmetic. It simply means the set of all possible ordered pairs, where the ordered pairs are something from A, comma, something from B. There are 4 choices for something from A. There are 3 choices for something from B. So there are going to be 12 distinct ordered pairs here. So this is going to take a little bit, but we could do A, comma, A. So the first thing has to be from the first set. So this is in A, this is in B. Little a is in capital A, little a is also in capital B. For the same choice of little a out of capital A, however, I could have chosen little b or C. So now for the same first choice from the set A, I have 3 possible choices from the set B. So I'm just going to keep listing things out. For the first set, I could have chosen B. For the second set, I could have chosen A, or I could have chosen B, or I could have chosen C. From the first set, I could have chosen C. From the second, I could choose A, or B, or C. And from the first set, I could have chosen D. Then from the second, I can choose A, or B, or C. We were expecting 12 things. Let's just count to see if I missed any. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Nope, got them all. Great. So having constructed this product, now we can attack this product here, but first we need to construct C intersect E. So C intersect E, I'm looking for things that are in C and they are also in E. So out of 1, 2, 3, 4, 5, what is also in the set 1, 7? Well, the only thing in there is 1. Now I can take the product E with the set we just constructed. This one's a lot faster because E only has 2 elements in it. This intersection only has 1 element in it, so we're only looking for 2 ordered pairs in here. The only choices I can make for my first element are 1 and 7, and the only choice at all I can make for my second element is 1. So E was 1, 7. This was only 1. So the only choice I have in the second coordinate is a 1, and then I could have chosen a 1 or a 7 in the first. Now we can construct this union. So I'm just going to list all of these and also all of those. So it'll take a little bit of time to write out. But E times C intersect E union A times B is just going to be all of the ordered pairs from the first thing, so 1, 1, 7, 1, and also all of the ordered pairs from the second, so AA, AB, AC, BA, BB, BC. What are we at now? CA, CB, CC, but then also DA, that's a D, DB, DC, and we got all of the elements out of both sets, and there we have it. All right, construct the set A complement minus C union B complement. So here the universe is important because A complement is everything that is not in the set A, which lots of things are not in the set A, but we're only looking for things that are in the universe that are not in the set A. So the complement of A is everything that's in the universe, but not in A. So looking at the universe, A, B, C, D, E, 1, 2, 3, 4, 5, 6, 7, A, B, C, and D are in A, so they don't go into the complement, but everything else from the universe does. Okay. We also need to construct C union B, so that's just going to be a list of everything in C and everything in B as well. Then the complement of those is everything in the universe that isn't what I just wrote. So in the universe, we have the letters A, B, C, D, E, but I'm not going to include A, B, C, so I only include D, E. In the universe, we have the numbers 1, 2, 3, 4, 5, 6, 7, but this set does have 1 through 5, so the complement is only going to include 6 and 7. Now for the difference of two sets, this set minus this one, I'm going to take everything that is in this set, but I will remove anything that I find here. Okay, that should have been a brace, my bad. So out of E, 1, 2, 3, 4, 5, 6, 7, I'm going to remove D, but hey, that wasn't there to remove anyway. I am, however, going to remove E, 6, and 7. So out of this set, A complement, if I remove E, 6, and 7, the only thing that remains is 1, 2, 3, 4, 5. Notice this happens to be exactly the set C. Okay, same things. Construct the set power set of E union power set of B. Power sets are just listing out all possible subsets. So the power set of E, well, since E has these two elements, I like to go by size. So first, how many zero element subsets are there? Just the empty set. How many one element subsets? I could have the set containing 1 or the set containing 7. How many two element subsets? Just E itself has 2 elements, so there is the only 2 element subset of E. You could have written this as the set containing 1 and 7, but we already have notation for that, that's just E. Okay, in general, the empty set and the set itself will always belong to the power set of something. So for example, for the power set of B, I know I'm going to need to include the empty set, and I'm going to need to include B itself. The empty set is the only set containing 0 elements that is a subset of B. And B has 3 elements, so this is the only set containing 3 elements that is a subset of B. But we got to build up our intermediaries. Sets containing 1 element could be A, B, or C. Sets containing 2 elements could be A, B, or AC, or BC. And now we have the only set with 0 elements, 3 possible sets with 1 element, 3 possible sets with 2 elements, and only 1 possible set with 3. And finally, we just take the union, so I'm just going to list all of these things out. I can write the empty set twice, but there's no necessary reason to do so. It's a little unusual. So I'm going to write out everything that is in both sets. It doesn't really matter what order I put them in, so I'll just put empty set, set containing 1, set containing 7, E. Then I could put the empty set again, but that would be redundant, so I'll just skip ahead. Set containing A, set containing B, set containing C, set containing A and B, set containing A and C, set containing B and C, and then the entire set B. Let's just double check that we get everything. We got those. We already had the empty set, those three, in the set B. Yep, everything's here. All right, so now we move on to proving stuff in set theory. So we have a conditional statement, if one thing and another, then something else. So we're going to do a direct proof. So we're going to assume the hypothesis, A is a subset of B and B is a subset of C. Now what we need to do is assert or claim that A is a subset of C. Now over on the right, I'm going to keep track of some formal definitions in terms of quantified statements. So we've already assumed this, which is to say, for any element of the universe, if it is in the set A, then it is an element of the set B. We've also assumed that B is a subset of C, so for any element of the universe, if it is in the set B, then it is in the set C. And now what we've claimed or asserted is that A is a subset of C. For any element of the universe, if it is in the set A, then it is in the set C. Notice that this is a conditional statement. So having asserted a conditional statement, we're going to assume the hypothesis. Okay, we want to later generalize to this universal statement, so we just need to make sure we use a variable as an element of A that hasn't been used for anything in our proof so far. So we just assume that something is an element of A. In other words, we've assumed this hypothesis, and the variable we used, little x, hasn't been used for anything so far in our proof, so we'll be able to generalize it to a universal later on. Now our only goal, having assumed this hypothesis, is to show this conclusion, x is an element of C. But we know if something is an element of A, then it must be an element of B. Why do we know that? Because A is a subset of B. In other words, we're going to use modus ponens. So we can say, since x is an element of A and A is a subset of B, x must be an element of B. This is how we would generally phrase this when we're actually writing out proofs, but this is just modus ponens. Okay? The hypothesis of this statement is that, and modus ponens gives us the conclusion, x is an element of B. Okay. Then we're just going to do it again. Since x is an element of B and B is a subset of C, x must be an element of C. Here we've just applied modus ponens here. But now what we've done is we've completed a direct proof. Anything that is an element of A is necessarily going to be an element of C, so we've completed this direct proof, and we indicate the proof is done with our little gravestone. Next up, all right, assume the hypothesis that A is a subset of B. Now what we need to do is show the conclusion. This set is the empty set. How do we show two sets are empty? That they are subsets of one another. But the empty set is a subset of anything at all. Okay? So as some notes, what we now need to show is that the empty set is a subset of this, and this is a subset of the empty set. Now, the empty set is always a subset of whatever I want. This is a tautology. Tautology. So there's really no point in writing it out, and no one ever does. Okay? You don't ever specify the empty set is a subset of something. Of course it is. So we need to show this. How do we show one set is a subset of another? What we would typically do is we would assume x was an element of this and then derive x as an element of the empty set. But that's pretty weird. We don't want anything to ever be an element of the empty set. This is why when we're trying to show something is empty, this statement is obvious. What we really need to show is that the set in question is a subset of the empty set. We tend to do it by contradiction. So our claim is this. Okay, so we claim that A minus B must be empty. Assume to the contrary that it's not. Well, what does it mean for a set to not be the empty set? That there is something in it. So there is some x which belongs to this set. Because it's not empty, there exists something in it. Well, if x belongs to A minus B, the definition is that X belongs to A and X doesn't belong to B. But look at our original assumption, A is a subset of B. X belongs to A. Since X belongs to A and A is a subset of B, we conclude that X must belong to B. In other words, X belongs to B and X doesn't belong to B. That's a contradiction. So having assumed to the contrary that our set wasn't empty, we got a contradiction. Therefore, this claim is backed up, and that was really the only thing left to show. So our proof is done, and we signal that with our gravestone. Next up, another claim that something is empty, so we assume the given A minus B equals A. We claim that A intersect B is in fact empty, but when we're trying to show a set is empty, almost always we're going to assume to the contrary that it's not. What does it mean for a set to not be empty? There is something in it. I just need to make sure I use a variable that hasn't been used for anything and X hasn't. Well, if X is in A intersect B, X is in A and X is in B. But A equals A minus B. So if X is in A, what do we conclude? That X is actually in A minus B. X is in A, which is the same set as A minus B, so X is in A minus B. What's the definition of X being in A minus B? X is in A and X is not in B. Now the fact that X is in A is redundant. We already had that. So this is totally optional to state. Okay? Most textbooks wouldn't write this out. They would simply say, since X is in A minus B, X is not in B, because that's the only thing that we actually need. Because we earlier had X is in B, now we have that it isn't. And that is simply a contradiction. So from our original assumption, we got a contradiction, therefore that assumption was wrong. So assuming to the contrary the set isn't empty, contradiction, therefore the set must be empty, proof is done. For our final problem, we are attempting to show two sets are equal. So to show two sets are equal, there are two steps involved. First, we'll show that the set on the left is a subset of the set on the right. Assume you've done all that. Then you would also need to show that the set on the right is a subset of the set on the left. If you can show both of these things, left subset of right and right subset of left, that would conclude the proof overall that the two sets are equal. So how do I show a set is a subset of another? I have to show that anything that's in this set must be in that one, and then I'll have to show anything in this set must be in that one. So we're going to go ahead and assume that we have an element of the set on the left. What does this mean? X is in A minus B, or X is in C minus B. I don't know which one. I need to now show that X must belong to A union C minus B, but we have this disjunction, one thing or another, and we know a conclusion we're working towards. That suggests we're going to do a proof by cases. First, let's prove that if the first thing is true, then after some work, we will show that X must belong to A union C minus B. But we can also show, suppose the second thing is true. Let's get exactly the same conclusion. Now I've left some extra space because we don't know exactly how we're going to get there. But I know this or that. We're going to do a direct proof, if this, then this conclusion. If the second possibility, then exactly the same conclusion. Then we can say, proof by cases, or in either case, X must belong to A union C minus B. And that will finish the proof of the left side. that this set is a subset of that. Starting with x in the set on the left, we will have shown that x is in the set on the right. Well, what if x is in the set A minus B? That means x is in A and x is not in B. What I'd like to conclude is that it is in A union C minus B, so the missing piece of information, I already have that it's not in B. The missing piece of information is that x is in A union C, and we already know it's not in B. Well, if x is in A, then either x is in A or x is in C. In other words, x is in A union C. So now what we have is that x is in A union C. We already knew it was not in B, so it belongs to this difference. Very similar argument will fill in case 2. Okay. So x is in C minus B means that x is in C and x is not in B. Well, if x is in C, then x is in A or x is in C. In other words, x is in A union C. If x is in A union C, and we already knew it was not in B, then we conclude that it is in fact in A union C minus B. This assumption got me to a conclusion. This assumption got me to the same conclusion. We know one of those two assumptions holds, so in either case, that conclusion holds. That finishes the proof of the one direction, that this is a subset of that. Any element of the set on the left is shown to necessarily be an element of the set on the right. All we have to do now is the same thing but backwards. So, assume we have an element of A union C minus B. We now need to do a bunch of work and show that x is in fact an element of A minus B union C minus B. If I can just get from here to there, that will prove this is a subset of that. Between the first and the second statements, we'll be done with our proof. All right, what's the definition of x is an element of A union C minus B? That x is in A union C and it is not in B. If x is in A union C, it's in A or it's in C. Okay, I've got a conclusion I know I'm working towards, and I have this disjunction here. So, case 1, maybe x is in A. Case 2, maybe x is in C. In both cases, I'm trying to get exactly the same conclusion, that x is in A minus B union C minus B. X is in A minus B union C minus B. If I can get from this assumption to that conclusion, from this assumption to the same conclusion, and I know one of those two assumptions must hold, I'll now go ahead and finish off by saying in either case, x must be in A minus B union C minus B, and we'd be done. So if x is in A, well, we already know x is not in B. So since x is in A and x is not in B, x must be in A minus B. We're trying to show that it's in A minus B union something else, and this doesn't really matter. If I already know it's in A minus B, then x is in A minus B or x is in anything, and that gets us right there. Similarly, if x is in C, I already knew that it's not in B, so I conclude that x must be an element of C minus B. Well, if x is in C minus B, then it's in some other random set, or it's in C minus B. I already know x is in C minus B, so I can do a disjunction with literally anything at all here and still be true. But this, x being an element of A minus B, allows me to go to x is in A minus B union C minus B. And that concludes the proof of this problem. Okay, a fairly lengthy one, and it does involve two separate proofs by cases, but there you have it.